We have not much time for going on with the cycles. A walk is closed if it has positive length and its origin and terminus are the same. So it starts and ends at the same vertex. A closed trail whose origin and internal vertices are distinct is a cycle. So a cycle resembles quite a lot a path, apart from the fact that origin and terminus are identical, okay? A path has no repetition of vertices. In a cycle, the only repetition is that origin and terminus are equal, but all the other vertices are different from them, okay? Just as with paths, we sometimes use the term cycle to denote a graph having as vertices and edges the ones of a cycle. A cycle of length k is called a k-cycle. A k-cycle is odd or even according as k is odd or even, okay? A three-cycle is often called a triangle. This is terminology just to speak in a faster way, but don't repeat me these things in an Excel, okay? You can see here an example of a closed trail because it starts and ends with U, but it has repetitions of vertices, so it's not a cycle, and a genuine cycle here, okay? And now a characterization of bipartite graphs. Characterization is a very precise term in mathematics. See, it means this. And you'll find, apart from my course and other courses, in mathematics you'll often see this situation. Something which interests you, bipartiteness. And you know what it is? The possibility of subdividing the vertex set, blah, 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 blah. Okay? You know very well what bipartite means. It's given only by the definition. But it might be troublesome to find the bipartition. And even more, to find that the bipartition does not exist. Do you see what I mean? If I find a bipartition, how did I solve the problem with the cube? Here is the you did it, maybe here, or anyway, I think you did it, okay? You gave me the vertices of x, you gave me the vertices of y. End of the game. It is surely bipartite because I just check that each edge connects x with y. End of the game. But how could you prove that a big graph with 100 vertices is not bipartite? Would you try all possible bipartition just to find that none is good because there is always one edge connecting x with x? That's too big. Okay, it's possible, you are in a finite case, but it's too big and too heavy. Maybe we can have something which is not the definition of bipartiteness, which is the thing we are interested in, but which gives us an if and only if. So a double implication. Bipartiteness implies this, and this implies bipartiteness. Let me remind you something. I am deeply a first-year teacher, okay, a linear algebra teacher. I'm interested in linear systems. I'm interested in knowing whether a linear system is solvable or not, okay? If I find an n-tuple which put in place of x1, xn satisfies all equations, the game is over. I've shown that the system is solvable since I have given you a solution, okay? But it might be too big, and it might be that the system is not solvable, and so I try 1,000 times and find no solutions. How can I do for finding if the system is solvable or not? Then there is a theorem which says, look at the rank of the two matrices, the incomplete and the complete, Rouchet-Capelli's theorem. Compute those two ranks. If and only if they are equal, then the system has a solution. Meaning, are you interested in the ranks of the two matrices from the beginning? No. Are you interested in the fact that the system is solvable or not? Yes. Now you have something you are interested in, solvability, but you know how to deal with. And then you have something which is seemingly meaningless, but which is easily computable, the two ranks. And then you have this if and only if. So if you want to know the thing you are interested in, solvability, you just look at the compute the two ranks, and you have the answer. Here we have the same thing. Please do not forget the definition of bipartite. This is not a definition of bipartite. This is a characterization, so a necessary and sufficient condition which we can use. So if I give you a big graph and you see a particular thing we are going to see, you can immediately see there is no bipartition. Don't try 1 million trials with your computer. There will be no bipartition. And this is it. A graph is bipartite if and only if it contains no odd cycle. Okay. Very, very often, these necessary and sufficient conditions are very asymmetrical here in graph theory. Not only in graph theory, but surely in graph theory. Generally, one way is extremely easy to understand, the other one is more tricky. And this is one case. Suppose it is bipartite, I'm going to show very easily that it has no odd cycle. But then we'll assume that our graph has no odd cycle, and we'll show that there is a bipartition. So first, G bipartite implies no odd cycle. Suppose G is bipartite with bipartition X, Y. And let's see V0, V1, Vk, V0 be a cycle of G. Without loss of generality, we may assume that V0 is in one of the two sets of the bipartition, say it belongs to X. But then, since V0, V1 is an edge and G is bipartite, surely V1 must belong to Y. Again, V2 must belong to X. And in general, V2I, meaning with in an even position inside this sequence, will belong to X, and V2I plus 1, meaning in a not position inside this sequence, must belong to Y. Since V0 belongs to X, Vk must belong to Y, then, which comes immediately before. Since we have an edge between Vk and V0, and so this means that since V0 we have assumed to be in X, Vk must necessarily be in Y, okay? But then K is some 2I plus 1 is in an odd position, and it means that we have an even number of edges here, okay? V0, V1, first edge, V1, V2, second edge, and so on and so forth. And so this Vk must be in an odd position, and this means that with the following edge you have an even number of up to Vk we have an odd number of edges, and then we have edge Vk V0, and we have an even number of edges. So however you take a cycle in G, this is necessarily even, has an even number of edges. This is the easy part. Let's say now, let's assume that for a connected graph, we assume that no odd cycles exist in this graph, okay? Now, choose an arbitrary vertex U, and now define a partition, and we see that actually it is a bipartition in our sense, but with this way. This is why we had to do the exercise on distances, okay? Because we need distance here. So let's put in X, we have chosen an arbitrary vertex U and fixed it, okay? Now we take in X all those vertices such that the distance from U is even, and in Y the ones for which the distance from U is odd. What is the distance? It's the minimal length of a path from u to x, from u to y. Okay? Let's show that this is truly bipartition. How can we do it? We take two vertices of x and show that they cannot be joined by an edge. Okay? All right? If we do like this, and the same can be done with y. If I take any two vertices of x and show that no edge can be there, then I won. So let's take v and w, two vertices of x. This means that the distance from u to x, from u to v and the distance from u to w is even because I put them in x, both in x, okay? So if I take p, a shortest uv path, that will have an even number of edges. Let's take a q, a shortest uw path, that also has an even number of edges. Okay. Now, of course, we can have a very simple situation like this. That we have u, we have v, and we have w, and we are very happy if we have p, which is this. 1, 2, 3, 4, 5, 6. And this is P. And then we have 1, 2, 3, 4, and this is Q. And so we are very happy with this, okay? Because then we can build a cycle, a path from V to W very easily, okay? But it's not always like this. We might have what? We might have this situation. No, let me do this. This screen is Q, and this red is P, okay? And we might have that these two minimal paths actually cross, okay? And so we cannot build immediately a path from V to W just by juxtaposing the inverse of one and the other, okay? As in the previous page, it was very easy, okay? I wanted to build a path from V to W, okay? This is a very comfortable situation, but we might have this situation, okay? So what? Let's see. Let U be the last vertex common to P and Q. Maybe the last vertex common to P and Q is U, as in my first example, or it might be this U1, okay? Then what can we say? Let's take the U1 section and of P and of Q. They have the same length. This is what I've done in my drawing. But why must they have exactly the same length? I have put here 3 edges and here 3 edges. Why not 3 and 5? I like very much this question. I repeat the setting. U, a fixed vertex. Here we have quite a lot of other vertices and edges, but in this big graph we don't see, we have that this P is a minimal path from U to V, meaning a path with the smallest possible number of edges. Here, from U to W, we have Q, this green path, which has the smallest possible number of edges for a path from U to W. Okay? We cannot say that they are disjoint as in this case, okay? They might have vertices in common. Let's assume that they have one or several, and let's take the last one that is in common. The book says this part and this part, the U1 section of Q and the U1 section of P must be of equal length. Why? They just assert that in a phrase. Why? Why couldn't I have here 5 green? Yeah, good. Assume that, then I'll make it, I'll go back, okay? Assume that we here have a piece which is of length 5. Then this green would not be of minimal length because I could build a Q prime which is shorter, taking this with 3 and this part. And so this would not be really a shortest path. So necessarily they must have this piece and this piece must be of equal length. Equal length, I don't know whether odd or even, but equal length. But then, what happens? What is the parity of the length of P and of Q? Remember, we have taken them from X, so W and V have an even distance from U. So the number of edges in P is even. The number of edges in Q is even. If I take away this part from Q and this part from P, I'm left with what? In this case, I've taken away 3 and 3, and so I'm left with something odd here and something odd here. But I might very well have, it would be legitimate to have 4 and 4, okay? And so I should have this because we have even distance from you, okay? But in that case, I take away something even here, something even here, I'm left with something odd here and something odd here. Meaning, this piece of P going backwards and this piece of Q have the same parity. Either they are both odd, as in this case, or they are both even, or they are both even, as in that case, or they are both odd, as in this case. And so, odd plus odd, or even plus even, always gives me an even path from U to W, from V to W. Do you see what I mean? So I take away all the part from U to U1 in both P and Q. I'm taking away the same number of edges both in P and Q, so I'm left with the piece of P which has the same parity of the piece of Q which is here. So either odd plus odd or even plus even. In any case, we get an even path from V to W. And so, what? So it means that we cannot have an edge from V to W, because if we had an edge from V to W, then we would have an odd cycle. But by hypothesis, we do not have odd cycles in our graph. And so V and W actually are not adjacent. There is no edge between them. So in any way I take two vertices in X, they are not adjacent. There is no edge between them. And in the same way, if I take two vertices in Y, there is no edge between them. And so actually what I built by this trick is actually a bipartition. And so the graph is bipartite, okay? Try to prove this, that if a small delta is greater than or equal to 2, then G contains a cycle. That's nice. Shortest path algorithm. Now we have one or two problems, but since I have only 6 minutes, I'll just start this problem, okay? And solution and everything and discussion will be next time, when we also have the possibility to compare this problem and this solution with another problem which is very similar and its solution. The problem here starts like this. We have a weighted graph. What does it mean, a weighted graph? It means, in this case, can be also a different thing, that we have some non-negative, let's even say positive numbers attached, one to each edge, okay? And this is the important difference from this problem to the next problem. We have a particular vertex. So when I'll ask you, what's the difference between Dijkstra's and Kruskal's algorithm? The main difference is that what we are going to look at now, solved by Dijkstra's algorithm, points out a particular vertex, which can be any of these vertices, but there is a vertex I am interested in. Okay, and it's very, very clear as what we have as an application. Dijkstra's algorithm, with very suitable many adaptations, is what is used by the navigators in your cars. Okay, and that's obvious then that there is a privileged vertex, the one we want to reach. Okay, actually in the navigator it works upside down, meaning here we want to start from a point and reach all other vertices, and in the application, the algorithm starts from our goal and comes towards us, okay? But the idea is there is a privileged vertex, and I want to minimize the sum of the weights. We call them weights, but generally we think of them as times of going through a road, or length of a road, or pay toll, what we have pay on the motorway for going from here to here and so on, okay? And we want to minimize the sum of what we pay, or in terms of these weights, from a privileged vertex to all other vertices of the graph. So this is the problem. Next time, in the next chapter, finally we go to another chapter, chapter 2, trees, we'll have a similar problem. We'll have again a weighted graph, and we'll build an optimal connector, meaning we want that everything is connected with everything, so it's possible to go from everywhere to everywhere, and we want to minimize the total weight of this connector, this general connector. So here we are not interested in minimizing in absolute terms, but to minimize things for U0. Okay? What is it? Think of Air France. Okay? Air France has a privileged vertex. Paris-Charles de Gaulle, okay? And everything is optimized for Paris-Charles de Gaulle, the main airport of Paris, okay? it has no meaning for Air France to think of optimizing a European net. They want to optimize connections with Paris Charles de Gaulle. And so what happens is that when I went to Singapore, so going east, I first thing went west because I went to Paris Charles de Gaulle, okay, where I took another plane which with a much longer trip took me to Singapore, okay, and which looks silly, okay. Why should I go west if I want to go east? Because everything was for privileging Paris Charles de Gaulle. I'm not so French looking, I'm Italian, so I cannot be French loving, sorry. No Italian is really French loving, okay? Uh, and so it is why, because Air France had the lowest price for me. And so I had to go there and stand the charm and kindness of French operators. Okay? And okay, so you can see this is for a privileged vertex. I am here and I'm not interested in minimizing anything. I want to minimize my trips from here to any other vertex in this. Next, we'll also see how to build an optimal connector which minimizes everything without a privilege for any vertex. Okay? Two different problems, two different, rather similar, but two different algorithms for solving them. Okay, see you tomorrow.